I explained the solution so clearly you know what I'm meaning. This is add edges to make degrees of all nodes even this evening. What do you perceive? Okay, there is an undirected graph consisting of n nodes numbered from 1 to n. Okay, you were given the integer n and a 2D array edges where edges of I equals AI, BI indicates that there is an edge between nodes AI and BI, right? So it's a very standard way that a problem is described in terms of a graph problem, right? You have this graph, you have these systems of edges that connect vertices of your graph, right? There's many problems that are introduced in this manner with this kind of information given. Okay. Indicates that there's an edge between nodes AI and BR. The graph can be disconnected, meaning that it's not necessarily the case that all vertices within your graph are connected, right? You could have some vertices over here and some vertices over here, right? And there could be no edges in between these different sets of vertices. Okay. You can add at most 2 additional edges, possibly none, to this graph so that there are no repeated edges and no self loops. Okay, so that's basically saying there's 2 things you can't do, right? There's 2 things that can't exist in this graph if you're going to add an additional edge. The first thing is if you have a node A, there's no such edge AA, meaning that there's no such edge that connects A to itself, right? So this is the first big no-no. You can't do that. And the second thing you can't do is if there's a node A and there's a node B, and there already is a connection between A and B, meaning that there already is A and B, this connection, right? I'm just specifying an edge as the left vertex and the right vertex as a list that the edge connects. If this already exists, you cannot add an additional edge between them, meaning that there's no repeated edges, right? Because what would this mean? Well, it means there's an edge AB, and then there's another edge AB or BA, depending on how you want to look at it, but these are intrinsically, right, the same edge. I've already connected A to B directly. I can't directly connect them again. So this is the second big no-no. And these are 2 things to think about when you solve this problem because it's going to come up. All right. So return true if it is possible to make the degree of each node in the graph even. Otherwise, return false. The degree of a node is the number of edges connected to it, right? So the degree of this node is 2, but we don't need to think about this because, this case can't exist. But, if you had a graph like this, well, let's just go ahead and look at the example, and then we'll talk about what degree means if that's not something you're familiar with. So in this problem, right, we have 1. That's not a 1. We have 3. We have 4. We have 2. We have 3 connecting 2. We have 5. We have 1. All right. So I'm just taking this example directly. Now the degree of each of these nodes are just the number of edges that connect to that node, right? So for 3, there's 1, 2 edges that connect to it. So it has degree 2. 4 has 1, 2, 3 nodes connected to it, 3 edges connected to it, so it has degree 3. 1 has 2 edges connected to it, so it has degree 2. 2 has degree 1, 2, 3, 4, so it has degree 4, and 5 has 1 thing connected to it, which has degree 1. Okay, now this problem is saying we want to return true if it's possible to make each node in the graph even, right? So we basically want to take this graph as it exists and say, okay, if there is a set of non-even nodes or one non-even node, whatever the number is, can we somehow add at most 2 additional edges to make that system have all even nodes? Essentially, right? Because if something has an odd degree, meaning that it has an odd number of edges going out of it, if we add an additional edge, technically that will make it even, right? So in this problem, we have the case, well, this is even, right? Because it has even degree, even degree, even degree. There's only 2 systems that have an odd degree. So in order to solve that, I think the most intuitive approach would be, well, what are some things that I can do actually? I mean, I think it's pretty intuitive, right? That you're just going to create an additional edge that connects these 2 to each other, right? Because now this will have degree 2 and this will have degree 4, right? And that seems pretty intuitive, but if it's not intuitive to you that you're supposed to do that, well, then think about the alternatives and what would happen. What would happen if we instead decided that it was a better idea to connect an odd to an even like this? Well, it is true that if something is even, if something is odd, this now becomes even, but the thing that was even before is now going to become odd. So we've just transferred the problem, right? We took something that was even and we made it odd, and we took something that was odd and made it even, right? So this was even, now it becomes odd. This was odd and became even. So I guess the first observation is, well, if you add something, if you add one edge, I guess is a better way of saying that. If you add one edge, right? So 1 to an even, so even becomes odd and odd becomes even, right? So that's kind of the first observation. So it's really easy to solve this problem by just saying, well, I'll just connect 5 to 4 directly. And since 5 was odd before and 4 was odd before, now they'll both become even and you'll be done, right? Let's look at another example here. Now for this example, it's a little bit different. And this is definitely the kind of problem where you kind of have to learn from doing the examples, right? There's a different weight or of importance corresponding to solving the examples based on the problem type, right? Usually it's a good idea to just go through all the examples because it can't really hurt unless time is a major constraint. But generally, some problems doing the examples will reveal a lot more information than other ones. And this is definitely one of those problems where doing the examples will reveal the solution to you more so than trying to think about instantly, given the description, what the solution type will be. Okay. So for this, we have 1 connecting to 2 and 3 connecting to 4. Okay. So for this problem, right, it's interesting because, well, they all have degree 1, right? So now we have 4 such systems, right? We have 4 such nodes where their degree is 1, right? So there's 4 odds. So you may be inclined to think, well, since 4 of them are odd and we can only connect 2 edges, right? There's not a lot I can do here in terms of making this even, right? Like, how can I make 4 things even? Well, we learned from this example, right? Just with 1 edge, we could make 2 things even if both of those things were odd, right? So if this was odd and this was odd, I can connect here, and this will become 2, and this will become 2, and this will become 2, and this will become 2. Okay. So then that's an example where 4 things are odd, and you can make it work by adding 2 additional edges. All right, now example 3, this is a false situation. So let's try to figure out why this is false versus the other examples are true. And then from there, we can kind of determine something more general about this problem, hopefully. Well, okay, the first thing here is this has degree 3, degree 1, degree 1, and degree 1. Right? 3, 1, 1. Okay. Now, what's the problem here? What's the difference between this one and the previous one? Right, so let's reorient this system so it's like this system, okay? So I'm just going to redraw this graph so it looks like this one. So then we can think about why this one doesn't work while this one does, right? Because this one is kind of the same situation if you think about it in terms of the degree of the nodes involved, right? This has degree 1, 1, 1, and 1. So it was odd, 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 and odd. And this is 4 odds, odd, 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 and odd. So there's 4 odds and 4 odds, but for whatever reason, with these 4 odds, you can make it work, but with these 4 odds, you can't. And why is that the case? So let's redraw this graph like this graph and see if we can use that information to determine some sort of intuition about how this is going to work. All right, so if we redrew this graph as the other one is, it was 1, 2, 3, and 4. 4 connects to 1. 2 connects to 1, and 3 connects to 1, and just like that. Okay. So why doesn't this work in this orientation versus this orientation? Well, let's think about it. We have 4 things that are odd, right? So we need to, I guess the idea is, well, you know, to make something even, you need to connect something to it, right? So in order to make one even, right, I'm going to have to make an edge come out of it. But where will that edge go, right? The problem with this case is, well, I need to connect something to 1 because it's odd. So I need to add an additional edge to make it even. Well, can I connect it to 3? No, I can't. Why can't I connect it to 3? Well, because remember we stated that you can't have repeated edges, right? So there's a repeated edge here, right? Okay, so that's a mistake. And I can't connect it to 2 because there's a repeated edge here. And I can't connect it to 4 because there's a repeated edge. So even though there's the same number of odd systems, since I can't repeat edges, I can't add any additional edge to this system, because in this system, it's the case that 1 is already connected to everything, right? So that's why this returns false. Okay, so that's kind of gives you a general idea, right? So this idea of there being no self loops and no repeated edges can create a problem with the total number of solutions that you can have, all right? Now let's try to limit what can occur in terms of where it could be the case that there is a solution and where there definitely isn't a solution, okay? Because depending on the orientation of the edges, if there's the same number of odd degree nodes, that determines whether or not there's a solution, okay? But let's try to think about more generally if we can exhaust to the individual cases that we have to look at in terms of the number of odd degrees, right? The first case is, well, if there's 0 odd degree edges, odd degree vertices, I guess. I don't even know how to spell vertices. If there's 0 odd degree vertices, we're done, right? If there's 0 degree odd vertices, then we don't need to do anything. We don't need to touch the system, right? If there's a system like this, we're done. We don't need to do anything, right? All these vertices have even degree, so we don't need to add any edges. So we're good, and we can just return true if that's the case, okay? What if there's only one edge that has an odd vertice? I mean, an odd degree. Ugh. This has odd degree 1, right? This has this has degree 3. This has degree 2. Is it even possible to have that? I don't even think that's possible. But if there's only one odd degree vertice, it has nothing to connect to. Right? If there's one thing that's odd and everything else in the system is even, well, this odd thing, right, regardless of how many edges it has going in, whatever, right? If everything else in the system is even, once this odd thing connects to something even within the system, this will become even, but then the thing it connects to becomes odd, right? So if you have one odd degree vertice, you have to return no, because there's nothing you can do, right? Because you have to add an edge to that odd vertice to make it even, but if you add an edge to the odd vertice to make it even, you're going to have to add an edge to an even vertice, which is going to make it odd, okay? And that's the same thing with 3 odd vertices. Now with two odd vertices, it's going to depend, right? We know that there are cases, right, where, you know, there was 2 odd vertices in this case and we were able to make a solution. But it might depend on the solution itself to determine if there's 2 odd vertices, if there's anything that we can do. So I guess it kind of depends. So we don't know. We have to put a, you know, we have to consider this later. Let's continue to go through the number of odd vertices. All right, if there's 3 odd vertices, well, you know, it's going to be just kind of like a case of this, right? Because when you make an odd vertice even, either you're going to connect that odd vertice to another odd vertice, which will make both of them even, or you're going to connect that odd vertice to an even vertice, which maintains the same number of vertices that are odd. So either you're going to have 3 odd vertices or 1 odd vertice, right? Because the only way you can get rid of an odd vertice is if you connect it to another odd vertice, which actually gets rid of 2 odd vertices, so then it just becomes this case again. Right? If you have, just as an example, I'm not going to give a proof, but, you know, if you have the case where, let's say you have 3 odd vertices, okay? So, okay. So in this example, you have 4 odd vertices. Damn it. Or how about this? And now these all have 2. It's crazy how hard this is, man. Right, so how many odd vertices do we have now? We have 1, 2, 3, 4. I don't even think it's possible to have. I'm starting to think that these cases aren't even possible. They can't even exist, right? Because I can't seem to find even a way to draw them. So I don't even think these cases exist. So you don't even need to think about that. It's impossible for there to be 1 odd vertice, right? Because if there's 1 odd vertice, it's going to have. There's impossible for there to be a non-even number of odd vertices, right? Because if a vertice connects to another thing, and that thing's even, then it has to connect to something else an odd number of times, right? But then an odd number of times. So I'm not going to make a general proof. Maybe later I will, but I'm starting to think that these things can't even occur, right? So there has to be an even number of odd vertices. And I'm not going to prove that, but I keep trying to draw out a system where there's an odd number of odd vertices, and it's just not happening. Okay. So then 2 odd vertice degrees. What if there's 4 odd vertices? Well, we've seen the case where there's 4 odd vertices, and we could make it work, right? Like here, there was 4 odd vertices, right? 1, 1, 1, 1, and we made it work. But in this case, right, there was 4 odd vertices in terms of the degree, and we couldn't make it work. So we could make it work with 4, and we couldn't make it work with 4. So we're going to have to put a pin in figuring out or determining whether or not we can make a solution here. Now, what if there's greater than 4 odd vertices? Or if there's 6 odd vertices, we can't do it. And why is that? Well, because we can only add at most 2 edges, right? So when we have 4 odd vertices, the idea is, right, for all these odd vertices, is that we're going to connect them to each other somehow. That way, this becomes even, and this becomes even, and this becomes even, and this becomes even, right? But if there's 6 odd vertices, there's still going to be another 2 that are odd, right? Because the only way we're going to make 4 odd vertices even is if we connect them to each other somehow. So then the 2 take care of each 2, right? One edge takes care of 2 odds, the other edge takes care of another 2 odds. But if there's 6 odd vertices, you can't connect to all of them, right? You need 3 edges in order to do that. So we can't do that. So then the only options we have to look at is, well, if we have 0 odd vertices, we return true. And if we have greater than 4 odd vertices, we return false. And then we just need to think about these particular cases in determining whether or not there's anything that we can do. So let's go ahead and start with that. And the best way, and what you're almost always going to do with these kind of problems, is you're going to convert the system into a adjacency list graph, right? Because processing it this way, we don't want to look at each individual edges. We want to look at the vertices and what's connecting them and how many neighbors they have. So we'll create this neighbors adjacency graph, and we'll just do it as a default dict. And then we'll have the neighbors be a set so that we can efficiently check people's neighbors, which will become important in a moment. And then we'll look at each UV edge, so each vertice connected by a pair and edges. And then we'll just say, okay, well, now the U has a neighbor V, and V has a neighbor U. Okay. Now, with that, we can say, well, we want to look at just the odd vertices, right? So we'll have O be the odd vertices, and we'll say O equals each of the vertices U for U in neighbors if the length of u, which is the degree, right? Because you add each of your neighbors connected to an edge, right? So the number of neighbors you have is just the degree of your vertice. So if the length of this is odd, and for the length of something to be odd, of course, you mod it by 2 and you get 1. Okay. Now we can play this game, right? If the length of odd is 0, meaning that we have 0 odd neighbors, we return true. If the length of odd is greater than 4, we return false. Now we just have to think about if the length of odd equals 2, we do something. And if the length of odd equals 4, we do something. And we've kind of assumed, but it seems intuitive, and there's probably a formal proof that I need to think about, that the number of odd can't be 3 or 1. So if it's greater than 4, then there's no way that we can connect all the odds to make them even. And if it equals 0, we don't need to do anything because it's already even. The system is fine as is. Okay. So, and then here we'll just return false. But this statement will never be reached, but just for the sake of this problem. Okay. So for this one, right, we're going to have this first case, which is the 2. So now we need to, let's just think about the 2 case first and handle that, and then we'll handle the 4 case and then determine if there's anything else we need to think about. Okay. So what are some of the ways that we could have 2 odd vertices? Well, we could have, something like this, right? In this system, right, there's 1 odd vertice, 1 odd vertice, and 1 non-odd vertice. Now, in this case, it's very simple, right? If you have 2 odds, then just connect them to make them even, right? If you have 2 odd vertices, just connect them and now they'll both become even and you're done, right? If you just connect both of these, now they're both even and they're done, right? But the caveat is what if you have 2 odds like this? Well, this has odd because the degree is 1, and this has odd because the degree is 1. But since they're already connected, we run into that initial issue, which is you can't have repeated edges. So you can't always just assume that because there's 2 odds that you can connect them, because they might already be connected and be odd. So we can do this if they're not connected, right? So I'm going to create a function called rConnected. I'll put it, I don't know where to put stuff anymore. So def rConnected, and it'll just tell you if 2 edges are connected. And what would it mean for 2 edges to be connected? That would mean that U is in the neighbor of V, right? Because that means they're neighbors, so they're connected to each other via some edge. Right, so that's the rConnected function. Actually, I think it's fine there. Okay, so if the length of the 2 are 2, well then, so we'll say U and V are the 2 edges that have odd degree, and we'll say if they're not connected, so if not rConnected, U and V, if they're not connected to each other, then we return true. Right, so that's the case here, right? Because they're not connected to each other, so we can just connect them, and now those 2 odds become even, and you're done. What about the case where they are connected already? Well, if they are connected already, the only way you can make this work is by connecting them to something else. But since they are connected already, they're the only 2 that are odd. So everything else in the system must be even. Okay? Because, right, we're in the case right now where there's only 2 odds, so everything else is even. So then, if I want to make this system even and this system even, well, I'm going to have to connect this thing to something else, right? Now this is even, but now that something else I connect to is odd. So we'll do that in a different color just because we like to be spiffy. Right, so if I connect this to something else, this is now even, but now this becomes odd. So the only way I'm going to make this work is if I then also connect this odd to that same thing. Now this becomes even. Now this becomes even. And this becomes even. Right? So the only way I can make a two odd system even if they're already connected to each other, if the two odds are already connected to each other, is if there's another node that both of them are not connected to that they can connect to together and make this triangle function, right? Because if this odd system, for whatever reason, was already connected like this, well, then it's just this problem again, right? Because then I can't create this additional edge to connect them. So there has to be another vertice that both of these things that can connect to, there has to be another vertice that both of these things can connect to that they're not already connected to, right? And if you can find that vertice, because since it's even, one of the odds can connect to it and the other odd can connect to it, and then everyone's even, right? Because the first one connecting to it makes it odd, the second one connecting to it makes it even again, and you just connected one edge to the initial edge, the initial vertice that was odd, and another edge to the initial second vertice that was odd. Okay. So if they're not connected, you return true. Otherwise, you'd say, well, return any W so it can't be connected U and W, and it can't be connected V and W for W in range, right? Because there's n vertices, 1 to n plus 1. So I'm basically saying we can make it work if there's another vertice W, right? This would be that vertice W in this case, right? If there's a vertice W such that our U isn't connected to it and our V isn't connected to it, right? If there's such a W that U is not connected to and V is not connected to, then we can connect U and V to it and fix this problem and make everything even. So if there's a W that U is not connected to and V is not connected to for all the vertices we can look at, then this is good and we're done. And we just return that. Okay. Now, if length of O equals 4, so that's everything in this case, right? There's no other way that we can make this work. And you'll notice here that when we run this, it should fix that first problem. Okay. Now we got to think about the for case. Well, in the for case, to make it work, we can't use some remaining edge, some remaining vertice W, right? Because we can only add two vertices. I mean, we can only add two edges, right? So in this case, when we did this, we took two vertices that were odd and made them even. But we need to make four vertices that are odd even. So the only way we're going to do that is if we somehow connect them to each other. Right, so these things need to somehow connect to one another. So how are we going to go about making that happen? Well, we need to somehow make these things connect to each other. So what are the conditions in which we can make this work? Well, if there's four odd vertices, right? So let's just say generally we don't know how they're connected in this system. So there's some system, maybe they're directly connected, meaning maybe these things directly connect like this, or maybe there's already an edge here. But I'm just saying that generally there's these four vertices, and they're connected in some way. Well, we need to somehow connect them so that we can make two sets of connections, and we'll call this one U and V and W and X, such that they're not already directly connected, right? Because we don't want to have this case. If these are already directly connected and they're odd, we can't add an additional edge between them. So we know that we're going to have to do some sort of connection between all of these nodes because we only have two edges that we can add. So how can we determine what's going to need to happen in order for this to work? Well, we can look at one edge and we can say, well, if U is not connected to V, U not connected to V, Well, then we can make it work by connecting u to v if w's not connected to x. If w is not connected to x, now we're done. Right, but if we try to connect u to v because they can connect and w can't connect to x, then that's not going to work. So we can either try to connect u to v and see what happens. We can try to connect u to w and see if v can connect to x. Right, so we basically we suppose the hypothesis, if we can do this, then can we do the other thing? Then it'll work, right? If I can connect u to w and I can connect v to x, then this works. If I can connect u to x and v to w, then this works, right? So the basic idea is you have these 4 nodes. You suppose one solution, and if it can work and the other one can work, then you're good. And there's only 4 such ways that this could happen, right? I could try to connect here, which would mean that this needs to connect here. I could try to connect here, so then this will need to connect here. Is there only 3 ways? Or there's only 3 ways that this could happen, right? Because I have any 3 that I could connect to, right? So this node can try to connect to this node, and that would have to connect to that. But that would only work if these edges don't already exist, right? So basically what we're checking is to see if in one of these cases, the edges that we're adding don't already exist to make this work. And these are the only 3 ways that you can make it work, okay? So basically what I'm saying is, well, let's say u, v, w, and x equals O, because there's 4 odds. And we could say, well, if they're not connected, u and v, and they're not connected w and x, we return true, right? Because then we can make it work. And we need to do this for all 3 cases. And if none of those 3 cases work, we have to return false because we've tried everything and we have. So u tries to connect to v, then w will have to connect to x. If u tries to connect to w, then v will have to try to connect to x. If u wants to connect to x, then v has to try to connect to w. So that's exhausting all 3 cases. And then this is this whole problem in the messiest of ways ever. All right. So this is kind of an interesting problem because I talked too soon and now I seem like a fool. R connected is not defined. Oops. Everything is not R connected. So maybe I should have done disconnected. But whatever, the runtime's amazing and it's okay. So what's the run and space of this system? Well, we have to look at all edges, right? And there's no repeated edges, so well, I guess everything can be connected, everything else. We have to look at all edges. So is it possible? I'm trying to think about edges in terms of vertices, n vertices. So all n vertices, in the worst case, connect to n minus 1 edges. So there could be n squared vertices at most. So we'll call that n squared. So n squared vertices, or nm edges, n plus m edges. So we'll do it like that. So we'll say that, So we'll say that n equals the number of vertices, n, we already have that, and m equals the length of edges, so the number of edges. For time, we have to add all the edges, so we have definitely m operations. And then we need to look at each of the vertices to determine the number of odd ones, so we have to look at n vertices. And then we just do a standard constant check to see if the number of odd is 0, greater than 4, 2, or 4. And then checking if things are connected is constant time, right? Because we just check if it's one of the neighbors in the set. So we check if something's a member of a set. That's constant time. So this is constant. So this is constant operation. This is constant, but we have to look at all n edges. So that's another n time, a constant operation for all n vertices. Sorry. So that's another n operations. And then this is a constant number of operations. So that's just m plus n time. All right. And then for space, well, we have to create a space in this default dict for each of the vertices. And then we have to create a reference to each of the neighbors, right? So that's m neighbors, and there's n vertices, so that's m plus n space as well. Okay. I could probably make this solution a lot shorter, but this problem's already hard enough as it is. I don't feel like going through that rigmarole. So that's it for today, guys. Hope you have a good one.